more to look at the overall canopy temperature, and then you would turn on the irrigation system, but not for individual plants, but for that whole area. Okay.
And second thing I would like to know, like when we do the storage of barley or wheat, and the innermost grains in that bin, if they have a little more moisture, right, the respiration rate depends on moisture as well as the temperature. And the innermost grains, they will have the high temperature, and then if the moisture is more heat will be generated, right? So we can know about that, okay, in this part of the bin, there is more heat, and it may spoil the germination capacity of that grain. But how to move that heat from that particular area?
Yeah.
So what type of system you use to remove the heat from that area?
So usually what is done is you would not remove the, usually you would, in a Canadian system, you would turn on the what is referred to as the aeration fan, and the aeration fan would then make the temperature uniform in that whole area, the whole bin. But that area would still continue to respire faster. So the easiest solution would be is, depending on how the bin is designed, if you like if it is happening in the center part of the bin, if you unload, take the grain out, one truck out, that spoilage part is the one which would come out first, and then you'll be able to remove that and then treat it outside. So that's what typically farmer would do. If they detect that kind of spoilage, they would do that by removing a truckload from that bin. Another way you can do that is, again, would be the aeration system, is where you could, typically you would insert a metal tube and then do the aeration just of that area, and then try to dry that grain in that area. Okay. Any other question on thermal aging? And as I said, once you have acquired the image, rest is the same. You then decide what features you want to extract, and what kind of classifier you want to build, what kind of analysis you want to do, and then do the classification. Okay? And if there are no questions, we move then to the hyperspectral imaging. This shows the hyperspectral imaging system in our lab. And again, in this particular case, what you have is again, you have the stand to hold the camera. So this is your camera, and this here, what I refer to here is the tunable filter, which allows to collect the images at any wavelength. The two black items at 45° angle are the light source. In our case, we are in halogen light source, which can direct light on the sample platform here. And because of two, it gives you more uniform light rather than using a single light source. Then the camera acquires the images, and then they go to the computer for processing. Okay. Now the hyperspectral imaging, so to understand this is, so like when we take the image, and we talked about the image as pixels, so XY coordinate, at XY coordinate we had a single value. Because every pixel had one value, whether whether it could be the summation of R, B, or it could be, if you were looking just in the R wavelength, then it would be one value of R, or one value of blue or green. What hyperspectral imaging does is that the MHRD spectroscopy, which is used for detecting a lot of internal characteristics of the materials. So what it does is that at each pixel, it measures the full spectrum. So how would be, so if you take one pixel, and at one pixel you would expose that to different wavelengths. So you could expose to a light intensity of 100 nanometer, then for 200 nanometer, or even as close as 100 nanometer and 101 nanometer. So depending on how many spectrum you want, what level of details you want to collect in the spectra, so your intensity changes, and you expose the sample, that each pixel, to many different wavelengths. And when you expose, then the reflectance would be basically so how it reacts to different wavelengths in terms of reflectance, that's what you are capturing. So you are capturing not a single value, but spectra on each value. So like for example, and that's why you need the tunable filters, because your light is constant, and you are basically using the filters you are saying. So like the filters are nothing but almost like, so you, easiest way to visualize that filters would be is that if you had different color discs, for example. So if you are going to design a system where you expose the sample is being exposed to the light, but you only want to capture the red image, you would have a red filter. And then if you want to collect in green, you rotate that, you would collect in green. And if you have a blue filter, you can rotate and then you collect in blue. Similarly, you can collect in any other at any other wavelength. So this is, you are doing mechanical rotation of the disk is basically mechanically you are rotating. But if you do the mechanically, you can't do that. So because we are talking about nanometer in the imaging, you are going from even in the visible spectrum 400 to 700 nanometer. And if you want to do every 10 nanometer, you would need many disks, for example. So mechanically is not possible. The tunable filter, basically, these are the electronically tunable filters, and they allow basically to capture the information at that wavelength, and you can do as closely spaced as 1 nanometer. Typically, people would do every 10 nanometer. Okay, so basically, what you are capturing is a spectrum at every pixel, and by doing that, you can then acquire both the spatial information that would be like any other camera would do. But at the same time, you also get the information about the internal, and you take the picture, you get the picture basically. In the hyperspectral imaging, what you are getting is you are getting the picture of the object at many wavelengths. Okay. And because you are getting at many wavelengths, so those images would be stacked. So one plane you can use basically for doing the spectral or the spatial information, whereas the spectra is then on multiple wavelengths. So if you look at another way, is that a spatial image at any single wavelength, you can basically then do the spatial analysis similar to a camera image. Whereas the wavelength direction, you're looking at there's a spectrum here. So this is so if you expose the sample to 1000 nanometers, your reflectance is let's say 0.38. But if you expose that to about 1120 nanometers, your reflectance is down to 0.35. So it is basically you are exposing your sample to many wavelengths, and you are seeing what the reflectance would be at those wavelengths, and that's what is referred to as the spectrum. Why that is important is that spectrum becomes the signature of your material. So like wheat would give you a different spectrum than the barley would give. Or insect damage kernels would give you a different spectrum than the sound kernel would give. Fungal damage kernel will give you a different spectrum than the sound. Same thing the meat. The nice quality meat would give you a different spectrum than the spoiled meat or meat from a test animal. Damaged fruit would give you the same versus the sound fruit. So that's what you are now analyzing. So you are analyzing the information. So every pixel basically gives you that spectrum. And we are looking at it is like, so if you had the again a grain sample, and you could have kernels of wheat, but in those kernels of wheat, if there is a piece of a stone, so a stone would be made of, let's say, 50 pixels. Each kernel of wheat may be made of 50 pixels. So when you start looking at the spectrum, all the wheat kernels would give you a similar spectrum when you are doing the analysis, but the stone would give you a different spectrum. So by difference in the spectrum, you know that there is a stone in the wheat, for example. Now, in that example, you don't have to use the hyperspectral system, because the camera would hopefully tell you the same thing. But now consider that we were talking about yesterday that when you the cross contamination of varieties or cultivars, that's where I think the spectral, so the different cultivars have different spectrum characteristics. So you may be able to detect the cross contamination. That's when you would do this kind of system. What is spending cost to detect that cross contamination? Okay, so but in terms of the concept, so idea that every pixel, rather than having a single value, it has its unique signature based on the chemical composition of that material or of that pixel, chemical composition of the material at that pixel. Now, typically the objects would be made of 30 to 50 to 100 pixels. So all of those pixels hopefully would have similar characteristics, and you can use that for identification. Okay, clear?
So one image to another image, what is the wavelength gap? Like if we are taking one image at 235 nanometers, another image will be captured at 236 or gap of 8.
That's the decision you make as a user. Cameras are capable of doing, or I shouldn't say cameras, the tunable filters are capable of being tuned to 1 nanometer. Typically, most people would collect them every 10 nanometer. Typically, yeah. But the filters are capable of tuning to every 1 nanometer. Okay.
Can we combine the spectral data with the image analysis?
Yeah, but that's what this particular one is doing. So for example, you could use any of these slides, because this slide is basically equivalent to one image. Okay, so you can do the image analysis on this image and get the information. Just like in RTV, you would have 3 images like this. So you can do the analysis on R image or D image, B image, or you can combine the 3 together. So that's what you can do here. You can do the intensity calculation by combining intensity of all gray levels, for example. Okay.
This has to be combined on MATLAB?
No.
How to combine?
The data we can collect the spectral data as well as spatial data
From the single camera.
For example, you have a data.
Yeah.
Spectral of the grain and is using camera. Can we use?
No, in that case you would not be able to combine. You would have to analyze image separately and FIR separately. This one, the camera itself, that built-in capability to do the spectral imaging.
At all wave number it can do it?
It can do, yeah, like from, it can do, I think the cameras are available from 100 to 2500 nanometers. Yeah, so single camera probably won't be able to do all that range. So we have, in our lab we have 2 cameras, and they go from 400 to 1800, I think, or 1700. 950. Yeah.
And another one goes from 750 to
1000. Yeah, 600. So we are basically covering it from 400 to about 1600 nanometer.
What is the cost of the camera which is selling this?
These cameras, and then there is another one available which goes up to 2500 nanometers. So like from 1100 to 2500 nanometer. Typically, these cameras would be, I would say, between $50,000 to $60,000. 60,000, yeah.
The one bought last year cost around like 120.
120, okay.
From like 400 to
2500. So single camera goes from 400 to 25. So that's 120,000. $1,000.
to multiply by so it is
6 lakhs.
No, we have to multiply 50.
yeah, we are 60,000.
60 lakhs. 60 lakhs. Yeah, but it has a lot of capabilities especially for search. So to give you the example, like so what you could do with a camera of the capability, you could identify, for example, here you could identify that for a particular sample there is a dip at about 1100 nanometer, and another sample may not have that dip. So all you need to then acquire the images at 1100 nanometer. Or you acquire the images at 1100 nanometer, and in that case you would basically buy a filter where you would use to acquire the image at that 1100 nanometer and then do analysis based on that 1100 nanometer. So that's where it becomes from hyperspectral. Hyperspectral means collecting image at many wavelengths, typically more than 100 wavelengths. And then if you use the hyperspectral to identify the significant wavelengths, and then you collect your image at those significant wavelengths, and it becomes a multispectral system. And typically multispectral bodies will be 3 to 5 different wavelengths where you could have and use that for your classification. Okay. So is the concept clear? Hyperspectral. Okay. And then this is showing you further that how you would like again wavelengths go in the jet direction, and then how the spectra would look so in this case, this is the looking at the reflectance for each pixel, and also look at absorbance for each pixel. So you can either capture the absorbance or reflectance from that at different wavelengths. And this is the other way of trying to explain is the how you visualize that is that for each pixel you basically can distribute color in this direction. Okay. So the hyperspectral system provides the size, shape, appearance. Is everybody okay? Yeah. So the hyperspectral system provides then the size, shape, appearance, and color information, which is basically by using any of those slices, and the chemical composition because of the spectral information it's providing. Now the element in the hyperspectral imaging, in the image, a two-dimensional image we call pixel. In the hyperspectral imaging it becomes then voxel. Okay, just the term is changed. As I said earlier, you can apply that from UV to infrared regions of from 200 to 2500 nanometer. And as Chala was saying, the camera we just bought goes from 400 to 2500 nanometer. Okay. But and hyperspectral imaging is used in many fields, in agriculture, in geology, medicine, pharmacy, food industry, and I will talk about my examples in the rest of the presentation. Another thing to keep in mind, there are 3 different approaches you can generate the hyperspectral image, because keeping in mind that you're doing every pixels, either you can do a point scanning, which is referred to as whisk broom imaging, or you can do a line scanning, which is referred to as a push broom imaging system, or area-based imaging, where you're taking the picture of the image and many wavelengths, and then it's referred to as tunable filter, because that's where how you're exposing your sample to different wavelengths. So you can present that way. This is the again a schematic of the hyperspectral imaging system which I showed you earlier. So you would have the sample, you have the platform, you have a sample, lighting source, your infrared the hyperspectral camera, and the filtering system, and naturally you would need the proper lens. So you can do the collection of the images. The tunable filters which I mentioned, there are commonly used electronically tunable filters are the liquid crystal tunable filters referred to as LCF, or there are acoustic tunable filter or interferometers. Most commonly used tunable filters are probably the liquid crystal tunable filters on the systems, and they give you tunability to basically at 1 nanometer level. And then once you have acquired this spectral data, so now you would have so much information, because every pixel would have that line information, so it's a lot of data. So to analyze data, you have to reduce the dimensionality of the data, and you can use the linear and non-linear approach. But most widely used, the transformation is the principal component analysis. And if I will take you to the, like when I was showing you 3 color data, and when you projected that on one axis, they were very easily separated. That would be almost like similar to showing the principal component, and then other one was not showing that variable. So you try to find the components, to take all this data and do a principal component analysis. Again, that's available in the statistical tool, and then from that through the orthogonal projections, you basically try to maximize the information you use for classification. And then you can move from hyperspectral to multispectral by identifying the significant wavelengths. So when you do the principal component analysis, you would basically then would do the so typically you would have 3 principal components or 2 principal components, which might explain the most of the variation in the data, like 96%, 95%. and then, but you can go to any number of principal components, and then you produce your image in those different principal components. So this is the example of the first principal component. When looking at first principal component, how the images would look like of different samples. Just to give you an example, you can similarly plot these images for the second principal component or third principal component, and then you are analyzing these images rather than analyzing the original image where you have the huge amount of data. Okay. You still would have to do the calibration, so similar to the which we talked about for the image, imaging in the visual spectrum. You could use a coin or any object of known dimension, but pick the object which is easily available to everybody else, so you can repeat and verify your results. You have to do the standardization of the illumination. We talked about using the Kodak card, white standard, for example, of known reflectance, and you can use that information. You can do the like LabVIEW data acquisition platform, where you can use the LabVIEW to acquire the images and store the images, or you can write your own data acquisition program. Sometimes the camera system would have their own image acquiring software built in, so you can use that. And once you have collected the spectral information, then you would actually run samples. And this example given here, you would have 300 random particles, and then you would put them on the background, the background, and take the images under using the hyperspectral camera. Okay, so that's what basically you would do. And with the you can use the MATLAB program and to read those files you are saved, and then do the basically analysis where you would do the labeling, background separation, which is segmentation. You would do normalization for intensity, reflex data, and use the information from the images for developing classifiers. And you can do two-way, multi-way classifications. Two-way classifications could be between just two object types, or you can have multiple objects and do the analysis. So if there are 6 classes in the picture, you would then do X-way classification. You would have to again have the training and testing set. So typically, if you are acquiring images from say 1,000 kernels, you might put 800 as a training set, and then test your algorithm or classifiers on the remaining 20%. The one thing which you need to keep in mind is that if you did the analysis only once, then you would basically get one output. But if you randomly select different training numbers, so out of 1,000 kernels, you randomly select 800 for testing or training and 200 for testing. Then the next time you select different 800, or again go again for selecting 800 randomly your training set, then 200 would become testing, and you do that multiple times. You would then you can get an idea that your training set is not affecting your output, so you can get the mean and a standard deviation or the variance on your results. So you say like if you ran that 20 times, you would have 20 classification results for the same raw data, and then you could say that our mean value of classification is 96%, but plus minus 10 deviation this based on 20 times you run the classification. So you could do that. And then for the performance evaluations, basically you are then comparing that with your classifier output. Okay. So this some example, like this particular example, when you do the multi-way classification, it is identifying by using different classifiers. So we talked about support vector machine or Bayes function classification or nearest neighbor classifier. And what is identifying is the basically the foreign material from wheat. So A is the wheat results for identifying the wheat using the raw NIR images, whereas the B is based on the Fourier descriptor, and then these are different classifiers basically, and giving you the information about the results of the identifying the foreign material in the grain sample, okay, or contaminants in the grain sample. So you can do similarly on classification on dog days, and there's another example of similar results for dog days, and you can do similar classification even on animal excreta, which could be present in the grain samples and give you the output. And the arrows basically are showing roughly where you got 100% classification. Okay. Another example is the detection of the insect damage, which has a significant impact on the grain industry, and it could result in the loss of weight, the nutrient germination, poor bread making flour. Typically, right now you would use visual inspection or sieving, flotation, Burley's funnel, temperature-based thermal imaging, X-ray, and infrared spectroscopy for detection insect damage. But you can also do that with the hyperspectral imaging. So similarly, fungal damage, which could result in the germination loss, discoloration, dry matter loss, increase in the free fatty acids, heating, mustiness, production of mycotoxins even. And as you know, mycotoxins are carcinogenic, so carcinogens. So you don't want to have that in the grain, otherwise it can affect the human health as well as the animals which are eating that grain. Microbial. So currently, the fungal damage is assessed by doing the plating, the culture method, or the microbial culture method, microscopic detection. You can use X-rays, thermal imaging, NIR spectroscopy, ultrasound, machine, but you can also do that with hyperspectral imaging. And sprout and mist damage, the same thing. The sprout and mist damage, they decrease the sprouting, and early sprouting basically it has more mileage, and then it can basically lower the quality of the flour when you want to make bread. And then similarly mist damage, where you have a shriveled kernels. And currently, usually that estimation is done using visual inspection or falling number method, X-rays, NIR spectroscopy, but you can use the hyperspectral imaging. So in this, the next few slides, that gives you basically the analysis of the insect damage kernels or fungal damage kernels, and this just gives you the details which insects were used or which fungal spores were used in that analysis, and then sprout and mist damage kernels collected from different locations in the region, and the healthy kernels were used, basically the Canada West particular variety in that example given there. So using the hyperspectral system in the two ranges, the long wave and the short wave, that basically is different ranges of spectrum were used for collecting images. So this just showing those two different cameras. You can also superimpose on top of that color imaging. So we are analyzing these sprout damage and damage kernels, so you can have images from 3 different cameras. Then you run the analysis. So in this particular example, using the back propagation neural network, these are just giving you the results. If we're just using the NIR, then the classification results, as you can see, are around 72%. If you were to use just the color, still higher. But when you combine the 3, then the classification results improve. So that's where the combination is coming, is by combining the features. And then you can see the classification on the insect damage kernels. Similarly, you can see that for fungal damaged kernels, and using different classifiers, linear, quadratic, and homologous between the healthy and the fungal damaged kernels, but 3 different fungal species. And you can see the results are quite significant, like quite high. Similarly, you can do the mist damaged kernels, and again, you see the results quite high using all the classifiers for the sample coming from different regions of the country. Another thing is the hyperspectral imaging can be used for detecting ochre toxin, which is produced by Aspergillus and Penicillium genera. And in Canada, the ochre toxin is usually produced by Penicillium vercosum, and that's the main species produce that. But it is a very significant problem. If you have the ochre toxin, then again in the Codex Alimentis specifies the limit of 5 ppb in your sample. If your ochre toxin is more than 5 ppb, they will not again accept the gain. So it is you have to detect that very accurately, and found in barley, wheat, rye, and coffee, for example, in different climatic zones, and then you need to detect that, and this particular one is hepatotoxic, immunotoxic, or teratogenic, just giving information on toxin A. These are the toxin detection methods currently used in the culture method, which is very time consuming. PCR can be used. Polymerase chain reaction system, again takes 24 hours. You can use the volatile component organization using GCMS, again requires time and is processed. Typically you would, when you do that, you need the extraction time, cleanup time, and then the detection time, and be detected at an earlier stage. If you detect the mycotoxin at an earlier stage, you basically can then take the corrective action, so you don't contaminate large quantity of food. So in this case, how you produce then the mycotoxin contaminated samples, you would